We're going to talk about convolutions. What this comes from is where we were on the last video, um, thinking about the solution to a particular initial value problem, forcing a spring with a general forcing function. And that's going to it leads us right into the general idea of a convolution of two functions. So the new PDF, this is based on handout number 2. There's a short link for it. That's a lowercase k, that's a capital K. But it's easier it'll be in the description. You can just copy it out of the description. Or hopefully it'll be linked from the description. So it's all going to be based on this handout, which is called Introduction to Convolutions. So we were at the point where we had a mass spring system, and we had a conjecture. It's definitely haven't proved it yet, that if you have a general forcing function, and you know the response to the hammer blow, let's say for our system with no damping, it starts moving and then oscillates forever. There was a combination of these two functions that looked like this. It was an integral. And I went ahead and went from minus infinity to infinity. We'll talk about the limits a little bit. Of f of tau and the hammer solution of t minus tau d tau. And that's called the convolution of those two functions. And what we're going to do is spend some time investigating just how to think about that and some properties. And there's lots of wonderful properties, but we're just going to do some of them. So the definition in general, like it says in the handout, as usual, the intention is ideally, you would look at that handout and really try to do it all together, and I'm just helping with the solutions and some comments about that. So you take the two functions, and the convolution is just indicated by a little asterisk, and it's the integral over the whole real line, and if you've seen it in a different way, we'll address that in a second, of f of tau g of t minus tau d tau. Now this looks asymmetrical in f and g, but eventually we'll show that it's commutative, that you can switch the f and g. But and it's not hard to prove, but I want to postpone that a little bit because I want to get really concrete as quickly as possible. One thing I want to do though is clear up a possible confusion because I'm coming from the world of ordinary differential equations and initial value problems in terms of how I'm presenting this, and because I'm referring to texts like Edwards and Penny, for example, I want to clear up something. These limits you don't always see. If you look up the definition of a convolution, depending on the context, you won't always see minus infinity to infinity here. So here's the deal. This is always the right definition, but so here's number 1. This is the solution to number 1. If f and g vanish, if they happen to vanish for t less than 0, then, well, let's see, what do we get? Then this integral, it automatically cuts down the region of integration. It's a very common phenomenon we're going to have lots of times when functions vanish outside of some region or some interval, and it has the effect of just changing the limits of integration. So when tau is negative, f is going to vanish, so this guy is going to be from 0 to infinity of the same thing. Okay. And when t minus tau is negative, it's going to vanish. Well, that's when tau is bigger than t, and so it's just really going to go from 0 to t. And this definition is often what you'll see as the definition of convolution in the context of initial value problems. And it's really just the same notion, and it happens to be applied for functions that vanish for t less than 0. For example, in Edwards and Penny, this is all discussed in the context of the Laplace transform, which we'll talk about, I think, rather later in the context of the Fourier transform. And that's a context in which it really kind of universally you consider functions that just vanish when t is less than 0. So that's kind of a minor point, but I wanted to start with that in case people had seen a definition and were thinking I was using something really qualitatively different or incorrect. Okay, so now I think you can get a lot of intuition for the convolution as I say in the PDF, as a weighted moving average. And we have to be to take that as a definition of convolution or a universal characterization of convolution, you have to be very, very generous about what you mean by a weighted moving average. In particular, we're going to allow averages that kind of can use positive and negative coefficients in their weightings. Although in most of the examples we're going to do in this handout, they'll be positive. Um, and sometimes this actually gets a little misleading, but it's a really good place to start. And so we'll look at some examples that do that. So we are going to take a little modification of our. We've already seen this. I've already been using this with a slightly different notation in the first handout. We're going to look at a rectangular pulse that starts at A and stops at B. And as we saw, often it's not so much the height of it, but the area that's important to normalize. So we're going to normalize that to 1. So in other words, the height is going to be 1 over B minus A. And then, of course, we have the step function that turns on at A. That's a really useful tool. That will have height 1. There's no way we could normalize that to have unit area because it goes on forever. Okay. And so what we want to do is we're going to look at f star g, and we're going to restrict it to the case where this is one of the functions. So we're going to look at what if we took f and we convolved it with, and we're even going to look at this a little simpler, r0 to a. Okay. So it's really going to be the pulse. We've been looking at this a lot. Pulse that starts at 0 and ends at A and has area 1. And what does this do? So the perspective here is, and we're going to play with this a little bit in the future, is that this is something we're modifying, some interesting function that we're modifying, and this is a simple and specialized tool that we're using to create a new function that's a modified version of f. As I say, we'll eventually realize, we'll see that you could actually think of it as this is being acted on and this is the tool. Or you could think of them as having more symmetrical roles. But I think it's really helpful to think about it in this somewhat artificial way right now. This is being modified. This is a tool. And we want to see, what does that do to f? What do you mean a modified version of f? Okay? And it's pretty simple because it's such a simple function. That's just f of tau. And then the values of that function are 1 over b minus a. And then it's times the unscaled function. That was with the capital A. And the thing about that is that has values just 0 or 1. Ooh, that's of t minus tau. It's probably not the last time I'm going to make that mistake while I'm writing and talking at the same time. This just is going to just change the limits of integration, as we were seeing, because this is just either 0 or 1. It's what's called an indicator function, or a characteristic function of a set. And that's what integrating against a characteristic function always does, just changes the limits of integration. So I'll give myself some room up here. And we're going to get integral. Okay, so when it's going to be when t minus tau is, ooh, that's 0a, sorry. And that's just going to be 1 over a. So let's move the 1 over a out. Okay, so t minus tau has to be bigger than 0. Okay, so tau had better not go above t. But it also has to be smaller than a. And if you think about that, that's going to start at t minus a. Okay, so, and then that's it. It's just that integral of f in that region divided by a. Well, that 1 over a, that's the width of that interval. And so we're going to get the situation where here's f. Actually, it could go on over here. Okay, here's f. And what's going to happen with f star, this rectangular pulse, at any particular point, t, it's going to look back by a, so this is going to be t minus a, and it's going to calculate the value of the new function here, it's going to look at this window, looking back by a distance a, and take the average of these values. And so that'll be maybe this high. Okay. Then for some other t, it's going to look back the same amount a and take the average of these guys. And maybe that looks like maybe slightly higher. And then here, it's going to take the average of those guys, maybe slightly lower. I claim that's going to smooth out things. I think it's fairly intuitive that if this has a bunch of little high frequency variation to it, that's going to almost disappear or be very much smoothed out. And so we're likely to get a rather smoother version of that function by smoothing it out, which is interesting because this is a discontinuous function. It's not smooth at all. And yet convolving with this discontinuous function can still have the effect of smoothing out f when we think of this as the tool and acting on the function f. So that's a lot of cool stuff about the convolution already. It can be thought of, at least in this particular case, and much more generally, as a weighted moving or a moving average. Here it's a windowed moving average, where the window is just from your particular time at any that you're evaluating the convolution back by a windowed moving average, and we could call it a lagging moving average. And so that's one interpretation. And this fact that we got smoothing behavior is going to be very, very general. It's hard to construct a convolution that doesn't smooth the factors of the convolution. We will, but it'll be very interesting. Okay. And as I point out in the text, this is exactly what you'd do in like a financial situation. If you have a super jagged function like the stock market, crash, crash, and you want to ignore some of the day-to-day variation, you would replace that with a moving average, and it's almost certainly going to be one of these lagging guys because you can't see into the future. If you're going to have like today's value, no, you shouldn't buy stocks from the person who claims that they can know what these values are. So that makes sense. But there's no reason mathematically we can't have a different kind of moving average that doesn't lag like that. Okay, so for example, let's just do B before this gets too long. Yeah, and then stop before it gets too long. So B is f star r minus a of t. So here's our function f. It doesn't have to be jaggy, but we'll imagine it's jaggy. And then our window function is from minus a to a, and it's the pulse of area 1. And then how do those combine? We're going to, at any particular time, I claim we're going to average everything between t minus a and t plus a and get the average value here, and then get another kind of smoothed out version, but looking backwards in time and forwards in time. So we can justify that pretty easily. This has a 1 over 2a to get the area right. So I'll set it up as minus infinity to infinity, but then we have the unnormalized one, and it's of t minus tau d tau. And again, if this is going to be between minus a and a, then tau has to be between t minus a and t plus a. And that's exactly the average value of f on this region here. Okay, so admitted, this is for a very simple one, the case where one of the functions is very, very simple. It's a unit area window function, piecewise constant. So this is a place where it literally is true that this convolution is a moving average. And it's going to be, in some cases, it's not quite as literally true, but it's still, I claim that this is more generally applicable than you might think, given this is such a special function. Okay, let's stop this one at this point.